All right, so welcome to Math Stat 341, probability. What I'm going to be doing today is talking about the German tank problem. This is one of my favorite problems to discuss. It seems like there's an issue right now with the sharing of the screen, so let me just quickly restore that. And so one of the things you'll realize as you get older is that there's very little specific material that you're doing in your classes that you're going to really be using consistently. What you're going to be using more is the mindset, the way to attack problems, and just knowing a little bit what's out there so that when something comes up, you know what to look at. I am about to recommend a book to you from a former student of mine who's actually a co-author on a paper I wrote on generalizations of the German tank problem. I trust him, I've known him for years, but I've only read about a fifth of the book, and I'm a little hesitant to recommend something until I finish it. So since my daughter has gymnastics today, I will finish it while watching her, and will probably make a book recommendation very, very soon. But the idea is to talk about how you already know enough to do useful mathematics to do research. I will be running research groups this summer on a variety of topics, including probability. So if anybody is interested in learning a little bit more about trying to hand at research, let me know. What I am presenting today was done by, among others, two students in my probability class a couple of years ago. So you already have enough to be useful. All right. Given the state of the American educational system, I'm not going to assume too much knowledge of World War II. I think I can still say US good, Axis bad. Okay, good. You're pretty much an ante for any conversation like this. So this is a map of Europe at the start of major hostilities. Again, you've got to be extremely careful what you mean when you talk about World War II. It was more than just Europe. There was also the Pacific theater, and the war there started much earlier than the land war in Europe. What you see is in a very short period of time, Germany conquered a tremendous amount of land. And a lot of this was due to their excellent use of tanks and tank tactics. And so here's a picture of the German tank production. It was extremely important for the Allies to know how many tanks the Germans were producing and how many were being deployed to various theaters. One possibility, of course, is to just go up to the Germans and ask, but that's probably not going to get you an accurate answer. How could you find out how many tanks the Germans were producing? What could you do? So one is to count what you see. What else could you do? Okay, so you can use the serial numbers, which is related to counting. So the Germans actually produced tanks and numbered them sequentially. And there's a lot of advantages to this. If the serial numbers are consecutive, then you know roughly by looking at a batch when was the tank made. And it can give you a quick idea of maybe when the tank is due for maintenance or various things like that. So this is going to be the math stats side, is looking at the serial numbers and saying, assuming the Germans have n tanks, and these are the serial numbers we observe, what do we think is the number of tanks produced? What else could you do? Well, but I'm saying, how else could you? Spies, you could use spies. And there's lots of ways you could use spies. You could have people who are working in the factory who are giving you information. You could also try to figure out what kind of supplies are the Germans getting and where are they sending the supplies. And if you have some idea of how much of various things are needed to make tanks, especially if there's certain key critical components, maybe engines, if you find out how many engines are being made, you might be able to use that. So there's a couple of different things you can do. It is a shame that it is cutting off a little bit at the bottom. Which do you think does better? Spies? I'm trying to see if that actually helps open up. Which do you think does better, spies or the mathematicians?
I think you saw this table actually. I think it's not by a long shot.
Wait, did we already do this lecture? Oh, we already did this one?
I don't know how much of the problem we did, but we definitely see.
I thought we just mentioned just a little bit.
Yeah, just a little bit.
Okay, just a little bit. Okay, so we've already seen a little bit of it, but we haven't done. Obviously it's going to be the mathematicians, or I wouldn't be giving this lecture, right? So let's assume we saw K serial numbers. We see K tanks, and you want to estimate how many tanks were produced. To some extent, this is a very common problem. So if I start talking too much about things we've already done, just let me know. Did we talk about tip jars at piano bars? Okay. When you go to a piano bar and you see a tip jar, the tip jar has money in it. It has money before the shift has begun. Why?
So it encourages people to get
It encourages people to give tips. And so people want to mislead you as to what is going on. Imagine you are trying to decide if you want to use a company and they tell you, we're really excited. You're going to be our first ever customer. Oh, really? So you want to often hide some information as to just exactly how many people have used your product. And so you may not want to have your order numbers consecutive. So there's lots of ways to encrypt information and whatnot. We will assume that tanks are numbered sequentially starting at 1, and we want to come up with some kind of estimate. So the original formulation was the tanks are numbered from 1 to capital N, and we want some estimator, and we often use hats to denote the estimator. That'll be a function on the largest serial number observed, little m, and the number of tanks observed, k. And then the new version, which I did with some of my students, is imagine that we don't start off at 1, but we start off at some number, and we go from n1 to n2. What would be the answer there? And it turns out the algebra is a little bit worse, but you can still get a nice closed form expression. Right. There are dangers of underestimating and overestimating. Does anybody want to give me a danger of either way? What could be bad?
If you underestimate, you're going to get destroyed by.
Yeah, if you underestimate, if you think there's only 100 tanks, you send 200 and you see 500 in front of you, it's bad. If it goes the other way, if you overestimate, you could commit too many forces there and you could lose the ability to make progress in other theaters. One of my favorite quips of Lincoln is, if General McClellan isn't going to use his army, I'd like to borrow it for time. So McClellan was terrific at training his troops, not so good at getting them into the field. And this was, paralysis by analysis, always thinking that the enemy had superior forces. And it led him to passing up on numerous opportunities to engage Lee at times that would have been opportune for him. And so there are tremendous damages that can happen when you have bad counts. It is essential to have good counts. Related to this, you have to be able to convince the powers that be to take your estimates seriously. And for anybody who thinks that this is just your professor doing theoretical babbling again, how many of you have experienced lockdowns due to COVID? So a lot of this was inspired by a British report, predicting millions and millions of deaths if the lockdowns didn't happen. And so the question is, can you trust models like this? What is wrong if the model is greatly overestimating or underestimating the consequences? I am not saying right now that lockdowns are right. I'm not saying lockdowns are wrong. I know this is being recorded. I'm just saying you have to be very careful when you have these models with predictions. And again, you often want to fail. Well, okay, you never want to fail, but if you're going to fail, certain directions are better than others. The classic example that should always be in your mind is an elevator. Okay, why am I thinking of an elevator? Yeah, you'd rather be too safe. And the elevator says 2,000 pounds and it can do 2,200, so it's a little bit under capacity. Then, oh no, it could only do 1,800, right? There is tremendous damage if you make the error in one way over the other. This is why for a lot of things, you're more likely to get a false positive and tell somebody that you have a disease than a false negative. False positive, we can do another test on you. False negative, you don't want someone going back out. So again, this is something to always be thinking about, which way, if you're going to have to make a mistake, do you want the mistake to go? Okay, so I'll talk a little bit about some of the mathematical preliminaries. A lot of this will be some similar slides, and we'll be able to do this pretty quickly. I'll talk about the theory behind the original and the new version, and then I'll talk about how we can use the method of least squares or linear regression to actually analyze this problem and to predict what the theoretical answer should be. And to me, that's one of the glories of this class, is that we can use this both for statistical inference and just trying to guess what the answer is, but we can also use this to help us prove things. If you have an idea of what the answer is, it's going to make it a lot easier to prove it. All right, so the first thing is the mathematical preliminaries. Everybody knows at this point in the semester, or you at least know enough to nod your head, that you know what the factorial function is, you know what binomial coefficients are, and you know what the binomial theorem is. All right, we've seen Pascal's triangle before. We've talked about proof by stories. Your n plus 1 choose k is n choose k plus n choose k minus 1. The new identity, I'm not going to go through the proof. Skip these slides. I'll skip these slides. The new identity we need is that the sum of m choose k from k to big N is n plus 1 choose k plus 1. So this is basically saying if I go down a diagonal, 1 plus 2 plus 3 plus 4 is 10, which is the next number to the right in the row below. 1 plus 4 plus 10 is 15. Another, again, proof by example. No, but it at least gives you some intuition as to what's going on. And this is one of just many beautiful relations in Pascal's triangle. Out of curiosity, has anybody seen this relation before? Okay. So it's a wonderful, wonderful relation. And it's responsible for the miracle that happens that gives us a closed form expression. So how many people are econ majors? Okay, so in your econ classes, if you're doing any modeling, you do not have a nice closed form solution for the economy where if I change this parameter, you know exactly what happens. You resort to simulations, you resort to lots and lots of trials. It's wonderful if you have a closed form expression and you can say, well, let me increase the money supply by this. Let me do this and let me see what impact that's going to have. We do lots of simulations with random processes and try to estimate what's going to happen. We are going to get a nice closed form expression as a function of K and M. So you tell me what K and M is, and I will give you a beautiful explicit answer. All right, so the proof of this identity is not too bad. It's a straightforward mathematical induction. So we first prove the base case. So when n equals k, there's essentially nothing to prove because the left-hand side is the sum from k to k of k choose k, which is just 1. And 1 is equal to k plus 1 choose k plus 1. And then like all these a large class of induction proofs, the way it proceeds is to now do the case for n plus 1, you isolate the n part and then add the next term. Well, by induction, we know what the first part is. It's just n plus 1 choose k plus 1. We then add n plus 1 choose k, and by Pascal's identity, we now get the result. All right, so here's the original German tank problem. Did we talk in the previous lecture about what we expect the formula to look like? Okay, we did. Okay, good. So that means I can do this part faster. So we know it has to be at least little m, and it should be some function of m and k. For a fixed k, the larger m is, the bigger our estimate should be. Similarly, for fixed m, the larger k is, the smaller we expect the answer to be. Imagine, I've observed m equals, 1,000 with k equals 1, or m equals 1,000 with k equals 800. All right, well, if, I have 800, I expect I should be pretty close to the largest with something like that. So something in the form b times m over k is quite reasonable. It turns out the actual answer is m 1 plus 1 over k, so basically b equals 1 minus 1. And we probably talked about how you can do sanity checks. You take one tank. If you take one tank, if there's 100 tanks of n equals 100, and you have one observation, you would guess you're probably in the middle. And so you would expect that you would have to double. If I have 100 tanks, I would expect my value of little m to be about 50, so I'd expect to have to double it. Good, 1 plus 1 over 1 is doubling this too. Conversely, if k equals n, that means you've observed everything. And then in that case, m is also going to be n because you've observed every tank. So the sanity checks work. All right, did we do this lemma that this is the probability that we observe little m tanks? Little m is the largest serial number. Okay, good. So let's calculate the probability that the largest serial number observed is little m. Clearly, little m has to be at least k because we observe k tanks starting at 1. It can't be larger than n because there's only n tanks. So I only need to find the probability between k and n. So there's two ways of doing it. The first is, well, notice I have a big N choose k in the denominator. Well, that's because I have n tanks and I have to choose k of them. So there's n choose k ways to sample. What you may be noticing is that this lecture is a great way to review what we've been doing all semester. We'll be reviewing expected value in a moment. This is one of the reasons why I love saving some of these applications towards the end so we can see how these tools are valuable. Now the top is that's how many ways I can choose m choose k. I can choose k tanks where m is the largest serial, where I do not choose a serial number larger than m. I choose k values from 1 to m. So the largest serial number is at most m. That doesn't mean it's exactly m. I then subtract m minus 1 choose k. That's the number of choices where the largest serial number is at most m minus 1. So when I subtract that, I'm left with all the choices where the largest serial number was m. Now, if I use Pascal's identity, that's the same as m minus 1 choose k minus 1. There's another way to do this. Well, if I want the largest serial number to be m, choose m. Once I choose m, I now have k minus 1 tanks that I must choose, and I can't choose a serial number larger than m minus 1. How many ways can I do that? M minus 1 choose k minus 1. You may actually prove the Pascal identity if you want by considering choosing tanks. So that's another way to essentially do what we just did, doing it as a subtraction problem rather than an addition problem. All right. So expected value, again, a great concept to review. The expected value of m is just the sum of m times the probability we take on the value of m. So we just put in the probability. All right, does anybody have any thoughts as to how we should try to work on this quantity? What's your first thought on something we can do? Hurry, the Germans are attacking. Come on, we don't have much time. What's your first thought as to how we could try to handle the sum? Who, the professor or the Germans? The Germans. Related to that, how many people have seen Patton? Phenomenal movie. George C. Scott declined an Oscar for his role there. My father's dentist actually served with Patton and said that George C. Scott did a better Patton than Patton. If he could have been like that 24/7, he would have. And there was a beautiful scene, early in the movie after Patton's forces defeat Rommel's in battle. He goes, "Rommel, you magnificent bastard! I read your book." So after World War I, Rommel wrote a book on infantry tactics. And there are some disadvantages in writing books on military strategy. So asking the Germans is not necessarily a silly thing to say. It was one of the best moments in the movie. So what's your first thought when you see this? What might you want to try to do?
Try to clean it up.
Yeah, so how would you clean it up? What would you do? So give me an explicit command. What should I do? Yeah, convert it to the factorial form, right? Let's put it into the factorials. We have an m minus 1. We have an m floating here. M times m minus 1 factorial will be an m factorial. So when you see this, expand it out. See if maybe you can make things nice. And now we just do a bunch of algebra. So when we expand it out, we have an m times an m minus 1. All right, we put everything together. I can pull out all the stuff that doesn't depend on little m, and I'm left with m choose k. Oh, I can sum this. That's the miracle I mentioned earlier. Right? So at this point, I just m factorial, k factorial, m minus k factorial, that's the coefficient. I then pull everything else up. And now I use the miracle. This is just n plus 1 choose k plus 1. I'm sorry that it's broken off at the bottom. I just substitute in what that binomial coefficient is in, and then I just do some cancellations, and it comes to n plus 1 times k over k plus 1. Fortunately, it's rewritten better at the top of the next page. So when we do all the algebra, and again, it was pretty straightforward algebra after we decided to expand the factorials, we get the expected value of m is k times n plus 1 over k plus 1. Well, that means we can solve for n in terms of k and m. And so n is equal to the expected value of m times 1 plus 1 over k minus 1. Well, what should we take for our expected value of m? Let's just take the value we observe. And in the statistics class, you will learn about all the different kinds of estimators, unbiased estimators and all stuff like this. What's the variance and what are the best estimators? So we're not going to get into that. But at an obvious level, I have to put in something for the expected value of m. Why not put in the value of m that I observe? And so there's our proof. Very simple in terms of m and k, and it does have the correct structural form. Wonderful. All right, we could look at the new problem. And so this is what I did with some students. And I want to just talk a little bit about how you would start it, but not necessarily do all the calculation. So now we have to be a little bit careful. The number of tanks is n2 minus n1 plus 1. So remember, if you go from 3 to 5, you have 3 tanks, even though 5 minus 3 is 2. So you have to remember the +1. Any Indiana Jones fans here? Raiders of the Lost Ark? You got to remember that 1 at the end. Okay. So I'm going to let S be the spread. M2 minus M1. What do you think the formula might be to estimate the number of tanks in terms of the spread? Before, we knew it had to be M plus, then we had maybe M over K, or some constant M over K. What would you guess here? Okay. Okay, so the number should be S, or maybe S plus 1, something like that, sure. And so how does the M over K change? We had M plus M over K, now we should have S plus. So how does M plus M over K change? The first M has to just be the spread, it has to be at least the spread or the spread plus 1. And what about M over K? What would you replace that with? So some constant times S over K. How many people think S over K? Something like that. But I claim it can't be S over K. Anybody know why it can't be S over K? Yes. S is not the number of tanks we observe. K is the number of tanks we observe. S is the spread.
It's S plus 1.
It's not okay. It's not S plus, I mean, S plus 1 is fine, but it's not the S that I'm worried about. In the S over K, I'm not worried about S, I'm worried about K in the denominator. I am going to estimate people's financial well-being in this classroom. And I'm going to need 1 volunteer. Do I have a volunteer? You don't actually have to say anything out loud, okay? Pretend you gave me your mean net worth, okay? Okay, so using his mean net worth, can I estimate the mean net worth of students in this classroom? Yes. Yes, and what would my estimate be? Yeah, whatever you told me, that's going to be my estimate. Is there any way in hell I should be able to estimate the variance in net worth from 1 observation? No. This is like when we were doing the method of least squares and we wanted to see how does the time it takes to roll down depend on the incline, but we always kept it at 30 degrees. We should never be able to sniff out how the time depends on the angle if we don't vary the angle. If I only have 1 data point, I should not be able to estimate a quantity like variance. So if I want to do something like spread, could I have a spread if I only have 1 observation? No. And so what I really need is the spread divided by K minus 1. Now, if I try to do 1 observation, just 1 tank, K equals 1, the spread would be 0, K minus 1 would be 0. I have 0 over 0. And the formula is basically telling me, don't even try it. It's smart enough to know that it can't do something in this case. Did I share the story about my brother and his friend with the baseball game with the super pitcher versus the super hitter? I think I shared this one. The hitter always hits a home run. The pitcher always strikes the guy out. This is the irresistible force meets the immovable object. What happens? There's a fundamental contradiction. In that case, the computer hung up for several minutes and eventually said, double. And viewed it as 4 bases for home run, no bases for an out. Let's split the difference. We'll give you 2 bases. You want to have formulas that hopefully know, do not use me in certain circumstances so you don't accidentally use them. The geometric series, what's 1 plus 2 plus 4 plus 8 plus 16 plus 32? It's -1. Because if you put in 2 to the geometric series, you get 1 over 1 minus 2. No. Now, it does make sense theoretically if you do algebraic number theory, but 1 plus 2 plus 4 plus 8 is not so large. It goes past infinity, comes in through -infinity, and then peters out a little bit before 0. You should not be getting an answer. But you can, of course, just still use the geometric series formula if r equals 2. It will give you a number, just the number has no bearing on reality. This formula is even better. It's going to give you a 0 divided by 0. So there's no danger of having anything from this. So S over K minus 1 is a much better answer in terms of what we predict. The actual answer is 2 over K minus 1. And if you think about the 2, that's actually reasonable because now I have 2 directions that I can be going. In the first one, I had a certainty that it started at 1 and I moved upwards. Now I can be moving in 2 directions. A factor of 2 seems reasonable. And again, you can check extreme cases. I'm not going to go through this in detail now. It's in the appendix and I'll send a link to the paper later. But we now have to calculate what is the probability that the spread equals S. And the formula you can see is a little bit more involved. It's not horrible, but it has a little bit more S dependence. And that's going to mean the algebra will be a little bit more painful, but it's not too bad. All right, so I'm not going to go through the details. You have to repeatedly multiply by 1 or add 0 in clever ways to facilitate applying binomial identities. All right, and I think I've shared this before. If you can trust these statistics, this is one of the greatest examples of just how powerful math and stats can be in terms of what the intelligence estimates were versus what the estimates of the math stats people were. And you're extremely close, within around 10%. So not bad at all. Again, the real challenge in a situation like this is, can you convince people? Have I shared the story of Midway from World War II? Right, where they had to convince Admiral Nimitz. And so, again, it's not enough to be right. It's not enough to know what to do. If you can't convince the people who make the yes or no decision, it doesn't matter. And that's one of the things to really learn. That's one of the values of going to a school like Williams, is you're not just taking math classes, you're not just taking stats classes, you're taking classes in a variety of fields. If you are on a sports team or in a club in a position of leadership, you are hopefully getting to the point where you can communicate well with people. We are the last department on campus to require students to do a public talk before they graduate. You have to be able, if you are going into the real world, to talk to people and convince them to listen to what you're doing. All right, so what I want to do now is turn to regression. And so I'm not going to go through these slides in detail because we've actually covered the method of least squares. So this is just going to be a really fast review of that part. You have a homework problem that's coming up. We chose to use the third method. You're using the squares rather than the absolute values because calculus is available. And so sadly, the dropped -1, the dropped inverse has continued on all the different slides. There should be an inverse on that matrix. We have explicit formulas for A and B. As long as all of the x's aren't the same, the denominators aren't 0 and the method actually works. And you have explicit closed form answers. This is wonderful. It means you don't have to resort to numerics. You don't have to resort to simulations. You can just write down what the best fit parameters are. We talked about how you can linearize many nonlinear relationships. If you don't get too much out of this semester, please have an appreciation for taking logarithms and you're converting relationships. All right, so we talked a little bit about Kepler's law. You're going to have your homework problem on that. You'll get something beautiful like this. We've talked about smooch, so I'm going to skip all that. We've talked about the birthday problem. Here is some data from the birthday problem. So if we tried and we believed that the probability of 2 people sharing a birthday is proportional to the number of days in a year to some power, if we take a logarithm, we now get a linear relationship. And when you look at the data, I did 2 different sets of 10,000 simulations where the year was chosen uniformly from 10,000 to 100,000. And for both of them, I got the index, the power A, was about a half. And remember, early on in the semester, we got that the number of people you needed for 50% chance was basically the square root of the number of days times the natural log of 4. And so again, just looking at the data, we can see the square root coming into play. And it's wonderful when the data can guide you in terms of what you're trying to do. You look a little puzzled?
I'm just wondering, it has a very interesting pattern. Do you have to, especially when you do linear regression, is that like looking at the residuals and stuff?
So there's a lot of great stuff here in terms of patterns. And so we'll see a little bit more of that in a moment. And then if that doesn't answer your question, let me know. But there's a lot of interesting information going here about how things are spread out. And is this indicating something? Are you more likely to have errors in one way or another. If we try to do things, well, I'll skip this one. I'll go to this one. This is a plot of n, the log of n versus the log of m in 1 over k for the German tank problem. And you see, looking at it like this, we really are seeing a nice linear relationship. And this is basically supporting the theoretical claims. What I want to do now is I want to talk about implementation issues of trying to estimate things. And I want to show you how statistics can help theory and actually suggest what we should try to prove. So here, I am trying to estimate the number of tanks as a function of the maximum observed with one tank, one value. And so theory is n is equal to 1 plus 1 over k times m minus 1. So I get a best fit line of 0.784 m plus 2875. What can you tell me about that best fit line? It is the best. Do you think that this can hold for all values of m? I've done the data in one region. I want to extend it to another. One of the few things I truly remember from my high school physics days is an amusing quote in our textbook. And it was trying to explain Einstein's theory of special relativity. How many people have done special relativity? If you haven't really seen the results, some of the results are a little bit surprising. And so the book had a line along the following effect. These results may seem surprising at first or counterintuitive at first, but you have to remember most people don't have experience traveling at 3/4 the speed of light. I like the use of the word most people. So some people have been traveling at 3/4 the speed of light. And so the idea is you take results in one region and you try to, yes, along those lines, whoever watched the original cartoon Super Friends for the Hall of Justice? One of the episodes I still remember all these years later is Superman is talking to the Wonder Twins. And he goes, "Great Scott, I promised to meet Wonder Woman on Saturday in 5 minutes." And he swooshes out, and he's going to be there. He's going to make it. It takes light. Anybody know how long it takes light to get from the sun to the earth? 8 to 9 minutes. He's going to get to Saturn, which is much further, in less than 5 minutes. And so, there are issues, shall we say.
Wow. If you're living in the DC universe, there's plenty of stuff to get ways to go around.
That is true. And I'll throw in the Marvel universe as well.
Yeah, God knows the Flash.
Yes. But let's go back to this question. If you're on a train and the train is traveling at 100 miles an hour, and you're on the train and you're jogging at 10 miles an hour, how fast does somebody on the ground see you traveling? 110. Roughly, it's not 110. Speed is not additive. Now, you're going to have to go several decimals deep before you see it's 109.9999997. As you get closer and closer to the speed of light, the defect gets greater and greater. Nothing, according to present theory, can travel faster than the speed of light. If you are only looking at things traveling at 100 miles an hour, the speed of light is 186,000 miles a second. 100 miles an hour is basically a standstill relative to the speed of light. Just because we have physical results that look to our level of precision that speed is additive at small velocities does not mean that speed is additive at larger velocities. It's the danger of extrapolating from one region to another. And you have to be extremely careful about that in life, that just because something works in this area does not mean it works when I move far away from that. When you look at 0.784 m plus 2875, if this were to work for all values of m, why would that be a problem? What would eventually happen? Yes.
Maximum observed tank is 0. You observe 0 tanks, but it says it.
Well, you would have to observe at least a 1, but so say you observe a 1. It would predict a large value, but if a large value is not terrible, But there is an absurdity that would happen. Imagine M is, yeah. So let's imagine M is, say, 1 million. What would you predict using this? If M was 1 million, what would you predict for M? Okay, roughly 784,000. You know the tanks are numbered sequentially. You observe a tank labeled 1 million, and you predict that there's 784,000 tanks. Bullshit. We know that the number of tanks has to be at least the largest. So this can't be right. The exponent, the constant in front of M is less than 1. So we know there has to be an issue. The issue is, what I'm doing is I choose capital N, and then I'm using that, choosing one value, and that's my M. I've actually flipped my X and Y axes. I really should be plotting the maximum observed as a function of N. I'm doing it this way because that's how we're going to do it in the lab, but it's causing a real problem. And this is not really discussed that much in stats classes. I really like highlighting how careful we have to be. Does it really matter which way I orient my axis? Well, my theory was divide, having the input variable over there. So yes, it does matter if you switch the order of the relationships. This is an absurd relation. If I go up to 2 tanks observed, it's a little bit better, 0.964, but it's still less than 1. If I go up to 5 tanks, well, okay, it's like the sound barrier. I've at least cracked the 1, 0.000 for my constant, but it's still a little bit lower. The correct value, sadly, it's cut off is 1.2. All right, so let's do it the other way. Let's plot the number of tanks on the x-axis and the maximum observed on the y-axis. And so now we have M as a function of N, which makes sense because that's how we're doing things in the lab. And the ratio should be K plus 1 over K. And so now, when we have K equals 1, I'm wondering if I typed something wrong here. I think it should be K over K plus 1. I think I typed it the wrong way upstairs. We should get 0.5N plus 0.5, we get 0.496. Very, very good. If we take K equals 2, it should be 0.667, we get 0.668. If we take K equals 5, 0.883, 0.828, again, very good. And this is the experiment we're actually doing. We're choosing big N and then observing little m. That's the relationship order we have. That's how the method of least squares was developed. Even though at the end of the day, we want to observe little m and predict big N, for the experiment we're doing right now, we're not choosing a little m and then estimating the big N. We're choosing the N, and then from that, drawing a tank and observing the little m. So it does matter. You have to keep track which are your dependent variables. Here is a nice trick that you can do that minimize a lot of the spread and the fluctuations. Let's go back to writing N as a function of M. And what I'm going to do is I'm going to run 100 runs for each value of big N and average them. And when I do that, that basically kills a lot of the fluctuations. And when I do something like that now and I try to find my best fit line, I should be getting 1.5 M. I'm getting 1.496. And so, again, things are working very well. This is, sorry, this is another typo. This should be K equals 2, not K equals 1, my apologies. But, the idea is by doing a lot of trials and averaging each trial, I can cut down a lot on the fluctuations. What I want to end with is, one of my favorites. So we know that N is supposed to be 1 plus 1 over Km minus 1. Does the minus 1 really matter in the limit? No. What really matters is the relationship with K and M, that it's 1 plus 1 over K times M. So let's see if we could sniff that out. So what I'm going to do is the x-axis is going to be K. It's going to be the number of observations. And the y-axis is going to be the best fit value of the slope. It's my best guess. Does anybody notice anything interesting about the best guess? So what do you think is going to happen as K gets larger and larger and larger? Yeah, if you look, again, we had that beautiful XKCD where they're breaking up. And one of the partners says, I agree with you that we should break up. I thought the statistics would convince you, no, it's not that. I can do better than someone who doesn't label their axes. Look at the axes. The label goes from 1.00 to 1.06. That's not a large spread, in the realm that we're looking at. It's unclear, but it seems reasonable that it might be converging to 1. Well, that's reasonable because we know it has to be at least, 1 times m. Does this look like it might be 1 plus 1 over k? Could be. What should we do to try to understand this? Take the log. Now, before we take the log, rather than looking at the best fit slope, what might we want to look at instead? Yeah, the best fit slope minus 1. If there's some known behavior, subtract off the known behavior and then analyze what's left over. So rather than plotting the slope or the log of the slope against the log of k, plot the log of the slope minus 1. So we look at the log-log plot, the log of a minus 1 versus the log of k. The best fit line we get is negative 0.999 log k minus 007, or actually 0.007. It's a nice twist. Anybody know the Bond reference in Star Wars Episode 7? You're lucky. They had the latest James Bond play a stormtrooper, and his number was, I believe, JB007 for his identification number. So this is just a pure coincidence that it's 007. What is the negative 0.999 log k though? What does that tell you? Yeah, it's basically saying if I exponentiate, then I basically get a minus 1 is equal to 1 over k. We have just come up with a theoretical formula just by looking at the best fit value for different values of k. It's amazing. Without doing any of the theoretical calculations, just by looking at some simulations, we are able to estimate that it should be 1 plus 1 over k times m. And now we can tell the theorists, this is what I want you to try to prove. Or you might just say, you know what, I'm convinced by this. Even if there's not a proof, I'm willing to use this. There are a lot of fields where we do not have proofs for relations. This is Williams, so you're supposed to be well-rounded. Who can tell me who David Hume was? Philosopher. Can you give me any of his famous theories that might be relevant to today? Something about a ship? So basically, if you take a ship and you replace it plank by plank by plank, at every moment in time, it's the same ship. But eventually, the entire ship has been changed. Is it still the same ship? So you can then ask the same thing about yourself as your cells die and whatnot and are replaced. At what point in your life are you fundamentally different than you were, say, 10, 20 years ago? Do you count as a new person? Are you some kind of continuum? So it all comes down to, these little changes. So one of his other famous things was that just because the sun has risen every day does not mean it's going to rise tomorrow. That said, if you had to put down a bet, which way would you bet? I would bet the sun is going to rise. We've talked a little bit, I think, about black swan events. It's a beautiful book about this. Did I give you the turkey example? So turkey comes into the world and is trying to make sense of the world. After a while, the turkey realizes that there are these strange creatures on 2 legs, and the purpose of their life seems to be to make me happy as a turkey. They bring me food, they give me shelter. And as the months pass, the turkey becomes more and more convinced that this is the nature of things, until sometime in November, when the turkey's worldview suffers a very radical change, right? It's the unlikely event. Well, it's actually not that unlikely. It's, for the most part, an annual holiday that happens every year. But until a certain point, you are not going to have the data to make that prediction. This is the danger I want to give you when you are looking at data. You have to be extremely careful in the predictions that you are making. If you are taking data in one region, you have to be very careful. State, these are the assumptions I am making. These are the beliefs I have, and if these beliefs hold, and if they continue to hold, this is what will happen. But they may not continue to hold. And so you have to be extremely careful. Special relativity is a great example that, in the initial data, it looked like speed was additive. But eventually it was discovered, no, speed is not additive. It's just we did not have machines that had enough sensitivity to detect that initially. And because we couldn't detect that, it made a lot of sense to believe, well, of course, speed is additive. And this is how you get somebody like Superman who can now fly anywhere in almost any speed. So thank you for wearing that shirt today. So be extremely careful about looking at one region and trying to extrapolate into others. That said, it's often not bad to try. Just be aware of what are the possible dangers. Do you think that there is something fundamentally new that's coming into play? How many people did Math 151 multivariable calculus? Do you remember Green's theorem and stuff like that? Yeah. I'm sorry? It was all the way at the end. And
My brain blocked out the last 2 weeks.
Yeah. And so the world is very different in higher dimensions. In one dimension, what kind of simple closed curves can you have in one dimension? So a simple closed curve is you have to return to where you start. So what are the only simple closed curves you can have in one dimension? Points. Because basically in one dimension, if you have a simple closed curve, you go out and you come back, it's essentially the same as just a point. So if you want to do calculus, the analog of Stokes' theorem on the line is the integral from a to a, right, of f of x dx is equal to big F of a minus big F of a equals 0. This is not a particularly exciting theorem. The thrill in the middle, it's not that exciting because there really is no interesting closed curve in the line. As soon as you go in two-dimensional space, however, we now have the opportunity of having more interesting closed curves. And now talking about what do we get if we integrate along the closed curve, interesting things can happen. And so if you just look at what's going on in one dimension, you're going to be misled as to what's going on. This is really, in some sense, a generalization of the fundamental theorem of calculus. It's just if you look at the closed form analog, the closed form analog is just so trivial on the line that it's not really worth discussing. All right, so again, a lot of points to have from this. The goal for the last few classes of the semester is to do application lectures, a mix of theory applications and a mix of applied applications, to just show you what stuff you've learned and how it can be used, to review the various things that we have done. And then if anybody is interested in doing some research over the summer, to give you a little bit of a sense of what my students and I have been looking at.